Okay.
Now I'm starting?
Yes.
Hi. We're going to get graphic. All right? So, what I need you to realize, boom, things you need to remember about these graphs is if this is your position on an axis, even though I'm labeling it a y, that's your position as you move horizontally. So I'm going to say where you are on an x-axis is what I'm plotting on a y based on a time in seconds. So this x is in meters. This time is in seconds, and if you're just walking away from something, as time ticks by, your distance away from it goes up. All right, now with this type of graph, or any graph really, there's two things you can do when you get graphic. You can get sloppy, which means how slopey it is. Unless you're in Columbus, it's sloopy. Or you can calculate area. All right, so with this one, what I do is say follow the letters. If you calculate a slope, it's always a y value, which in this case is meters, and then you divide it by an x value, which in this case is seconds. So it's a meter divided by a second, which is a meter per second. That tells you how fast you're going. So what your math teacher would tell you is the slope of the line is a change in y divided by a change in x. Just rise over run. I'm going to swapify that. I'm going to say the y-axis is clearly an x, a position. So this is going to become a change in x. And I'm going to swapify the x because the axis is now clearly labeled time, so it's over a delta t. So that's what slope is for this particular graph, delta x over delta t. So you guys all also know that your math teacher said, hey, this slope, when you calculate a change in, it's what, a y2 minus a y1. And this is an x2 minus an x1. And I will do the same thing with this. A change in x is your x final minus your x initial. And a change in time is your t final minus your time initial. If we assume we start at a time of 0, then your initial time is 0, so it doesn't matter. So it's an xf minus an xi over t. That's a change in position divided by a time, which is the definition of speed. So what I will do is call that the letter v for velocity. So what I have is an xf minus xi over t is clearly a v. What I will do is rearrange this because fractions were created by the devil. I will multiply the v by the t, and I will then push the plus button so the xi moves over. So this will be an xf, wherever you are, is this vt plus your xi, wherever you started, plus velocity times time. This should look strikingly identical to what I've called before Formula 1. It's the very first formula I gave you from our talking about this. This should also look strikingly similar to what your math teacher taught you the formula for any given straight line is, and that is y is clearly the same thing as mx, which I will use this as an mx and put the plus b over there just so it lines up with this formula a little more. And what you know this m is the slope, which is the same thing that the velocity is the slope of this particular line. So your slope times time, your velocity times time is however far you go, and just add wherever you started. Cool? Huh? Simple? So this then slope is the meters per second, okay? I'm not going to mess with calculating an area of this graph because area is multiplying a y by an x. And if you follow the letters, you would multiply a meter by a second, and that would just give you meter seconds. And those are very useful for for getting graphic. All right, so for this one, all we calculate is the slope. Now, what if I were to make a velocity graph based on this motion? That would be a pretty constant velocity. So, a velocity graph based on that in meters per second to time in seconds would be a nice flat horizontal line at whatever value that slope is. Whatever we calculate, let's pretend in our headsies just to keep it simple. I don't know, the slope is 3. Fine. What that means is I would go up here, boom, and it would be a nice flat constant velocity that as time goes by, and that velocity doesn't change. It stays at 3. All right? Now with this graph, again, you have two things you can do with any given graph. You can see how sloppy it is. You can get the slope, or you can calculate the area. If we get sloppy with this one, for example, you already know it's going to be a value of 0, but the way you calculate it again is the same way a change in y over a change in x. The y is clearly a velocity. The x is still a time in seconds. So this is going to be a VF minus a VI over time. A change in velocity over time, you know, is the definition of an acceleration. So this is the acceleration. So this should look strikingly similar to this, with just different letters in it. So this is where formula 3 comes from. What I will do is rearrange this. Again, because fractions were created by the double, I'll multiply the t over, and I will add the vi over. And so what this becomes is the vf is clearly the same thing as the vi plus at, the vi plus at, which again, hopefully, looks strikingly identical to y equals mx plus b, where again that slope is your acceleration on this particular graph, which makes sense because the slope is 0 for this example, which means we weren't accelerating, and you can tell you're not accelerating if that's a nice straight line that doesn't curve. All right, so there's that. Now, slope again tells you acceleration. The other thing we can calculate is area. So, all right, an area again is a y multiplied by an x. So if I want to calculate the area, I can take a base times a height, or a delta y multiplied by a delta x. It's this times this, which if you follow the letters now, I'm going to get a meter per second. I'm going to multiply that by a second instead of divide. So if it's a meter per second times a second, those s's die, and that will tell you how far you go if you calculate the area that you would shade under, you know, here, and say from time 0 to this time, there's your delta x, and there's your delta y. So area of a velocity graph tells you how far you go, and the slope of a velocity graph tells you your acceleration, okay? Okay, and then there's one more graph. If I were to graph the acceleration based on this, you know it would just be a nice flat horizontal line at 0, and there wouldn't be much to do because, again, you're not accelerating. But if we do have an acceleration graph to time, this is in meters per second squared. That's the acceleration. Time is still in seconds. If you're moving with a 0 acceleration, this graph would just be a flat line at 0. That makes sense. But what if we are accelerating at a constant rate? Let's pretend in our headsies we're accelerating at, I don't know, 2 meters per second squared. Then again, there's two things you can do with any given graph. You can calculate slope, or you can calculate area. Slope is, again, a y divided by an x. So if we get sloppy, that would be a meter per second squared per second, which becomes meters per second cubed, which we could talk about. Perhaps in more advanced physics class you will, but we usually don't talk about changes in acceleration here. All right? What we can also do is calculate area. So if we calculate the area of this, again, you follow the letters. It's a meter per second squared, but now we're going to multiply by a second. And when you do that, this s kills the square of one of those s's, and you're left with meters per second, so that's a velocity. So an area of an acceleration graph will tell you your velocity or your change in velocity because you are accelerating. All right, so can we go backwards? If you're accelerating at 2, would that give you a graph that looks like this? And the answer is no, it would not, because you're accelerating. Your velocity is changing. And if you have an acceleration of 2, then you already do know what the slope of that line would be. It's this many. It's a slope of 2. So what you would end up with is a line that looks like that, where the slope is 2 meters per second squared. That would be the slope of this line. And then can we go backwards again and say, all right, if that's the case, what would your position graph look like? And remember, how sloppy this is an indicator of how fast you're going. So if you're accelerating, you're starting out going not very fast, so this would start out being not very sloppy. But as time goes by, your slope would continuously get steeper and steeper, and if we can make those line segments infinitely short, you would end up with a nice curved parabola. So when you're accelerating, you can tell just by looking at an X or position graph, that's when they curve. When you don't accelerate, that's when they go straight. All right, so getting graphic, you got slopes and areas. If it's a constant velocity, this is a straight line. If it's an acceleration, it curves. And just remember, everything your math teacher, y equals mx plus b, is the same thing we're doing. The joke I use is your math teacher likes to be very Atlantic, meaning this formula is a very broad application. It can be applied to any graph that's a straight line. In physics, we get a tad more Pacific, which means this particular application is a distance wherever you are to that. And this application of it is a velocity, however fast you're going relative to that. But they're both different ways of saying y equals mx plus b. Yay, physics.